Hello, my name is Pranav Kanani. I'm one of the TAs this fall for the Deep Learning course at CMU. Karan and I would be walking you through the fundamentals of Numpy in this recitation series. Before we dive in, you may ask what Numpy is. Well, Numpy is a fundamental package for scientific computing in Python. It is a Python library that provides an assortment of operations for fast operations on arrays. These range from mathematical, logical operations to basic linear algebra, random simulation, and much more. We will be relying heavily on NumPy in this course, and it is important for you all to understand its overall concepts and the functions that we have on NumPy. This recitation series would cover the following contents: installation, initialization, accessing and modifying data using NumPy, pivoting data, combining data, and math operations. Moving on to installation. Generally, NumPy is pre-installed on Colab or AWS. It is hence essential for us to check the version of NumPy as some operations kind of get deprecated. The version can be checked using the command pip show numpy. If you do not have NumPy installed on your system, that's fine. You can install NumPy using the command pip install numpy. NumPy can also be imported once you have installed it using the command import numpy as np. np is generally an alias for NumPy, which is used to refer or invoke functions and operations that NumPy has to offer. Moving on to initialization. We can create different types of arrays using NumPy. I will walk you through the ones which we most commonly use. We can create an empty array using the np.empty function. Specifying the number of rows and columns as parameters helps create such an array. In this case, we created an empty array of 2 rows and 2 columns. Here is the output. We can also create a zeros array of a given dimension using the np.zeros function, and also a ones array using the np.ones function. The np.full function is used to create an array of a given dimension and fill that array with a particular value, which in this case is 10, as shown here. The zeros underscore like function is used to create a zeros array without specifying the size of the array explicitly. Instead of specifying the size, we pass another array as a parameter to this function. NumPy automatically references the dimensions of this passed array, in this case the ones array, and imposes the shape onto the zeros array. So in result, we get a 4-row and 2-column matrix with zeros. Similarly, the np.ones underscore like creates a ones array with the specified dimensions as of zeros underscore arr. The full underscore like also takes in a similar command, but we can also specify a new fill value using which we can fill the array with our own desired value. The full underscore like takes the first parameter as another array of a reference shape and imposes the shape onto the resulting array. The second parameter is the value with which we want to fill the array with. The D type is used to actually specify which kind of array we want. In this case, we need a double array. The output is over here. We can also use NumPy to create an array from existing data. Suppose we have a list of containing 4 elements and we want to typecast to a NumPy array. This can be achieved using the np.array function and passing the list as a parameter to this function. This automatically converts this list to a NumPy array and stores it in the variable arr from list. NumPy can also be used to load data from a text file. We use the numpy np.loadtxt function and specify the path to the text file to load the data into the array. We can also use the np.load function to load a numpy file containing elements into a variable. We can also create arrays for a given range. We can use the np.arange, which returns an evenly spaced array within a given interval. If I specify the parameter as 10, it creates an array of integers ranging from 0 to 9. The np.linspace function returns an evenly spaced array over numbers specified over a particular interval. In this case, we start from 2, end at 3, and we desire 5 elements in the array. We also have a parameter which says endpoint, which specifies whether we want the endpoint, which in this case is 3, to be returned or not. Since it's set as false, we only get values ranging from 2 to 2.8. We can also create an array with random values. Using the np.random.randint function, we can generate random integers from 0 to 10 and for this particular dimension. Here is the output. One thing to note in this kind of a situation is that every time we run this function, we end up getting a different output. For debugging purposes, it becomes difficult for us to understand how or where our own program is not working out. Hence, it's advisable to always set a seed. This seed allows NumPy to create a random set of integers which always stay the same over different iterations. So if I set the seed as 0 and run this function twice, I would get the same output, as you can see here. The np.rand function is used to create an array by drawing samples from a uniform distribution over 0 and 1. The 3 and 2 specifies the dimensions of the array, which indicates 3 rows and 2 columns. The output is shown here. The np.random_randint function again also helps create an array of random integers, as I talked about earlier. We can also utilize the np.random_rand function to sample values from a Gaussian distribution. We just simply need to specify the mean and the standard deviation and cast the entire mean and standard deviation along with the uniform distribution into a Gaussian distribution. We simply add the mean to the standard deviation multiplied by the value from the uniform distribution. In this case, if we desire a 2x4 matrix, we specify the 2 rows and 4 columns as parameters to the uniform distribution. We multiply it with the standard deviation and add the mean to get a Gaussian distribution as shown here. I will now be going through accessing and modifying data in NumPy arrays. Indexing values from NumPy arrays is almost the same as in Python lists. We have an array here which samples elements from a uniform distribution. This array comprises of 4 batches with 30 elements within each batch. These 30 elements can be segregated further into 5 rows and 6 columns. Indexing in arrays start from 0. So if we want to index the 3rd row, 4th column of the 2nd batch, we pass the following index. If we want to slice along a batch and return all the elements belonging to a particular batch number, this is what we do. Now, if we want to segregate elements belonging to the first 3 rows, first 4 columns, and belonging to the first batch, these are the indices we pass. We can also slice along multiple batches. This index pattern returns elements in the 4th row, the 5th column, across all the batches. Slicing can also be done at intervals. The syntax for slicing at intervals is as follows, where we provide the start, stop, and the step size all separated by colons. Now, if we want to print all the elements belonging to alternate batches such that the step size is 2, this is what we pass in the index. If we want elements belonging to alternate batches from rows 2 to 5 and columns starting from 1 with stepping at an interval of 2, this is the index. We can also modify NumPy arrays. To copy a NumPy array, we use the function np.copy and specify the array which we want to copy. To modify single values, we can pass the index at which we want to modify the value, and this is where the value changes. This is a simple check operation to see whether the value at n copy is the same as the value at n. Since we already changed it to 0.05, 0.005, the value is false, which indicates that the value has been updated in the array, as seen here. We can also modify multiple values in a NumPy array. Here we are looking at a small section of the data present in n copy and n. We know that these two sections are the same as printed out here. Before modifying the values, I just wanted to show how the values are in n copy. N copy contains these values. Now, just by specifying the indices, I have set all the values to 0.5. And after modifying those values, it became 0.5 as shown here. When we do a simple check operation to check whether the values are the same in both the arrays along those same indices, we get a false. This indicates that our values have been updated.